With probability, it can either be with or without replacement. And as you can see, this question deals with without replacement. Those type of questions usually are things to deal with food, raffle prizes, or anything that's destructive. Other types of probability are usually replacement, where you pick, say, a coloured disc out of a bag and you put the disc back. So that's the difference between with and without replacement. Now, as you can see, this particular question is about prizes being drawn from a box. There are 12 prizes, a book, 3 key rings, and 8 pencils. Now, this is an example of without replacement, because when you win a prize or you select a prize from the box, you do not put that prize back. So we need to look carefully at what the words are telling us. So as I've said, because it's prizes, that words are telling us that we are not going to replace a prize. Similarly, we need to think carefully about how we're going to organize our work. Now, as you can see, because they've said it's a book, a keyring, and a pencil, you do not need to write the full name of each prize. For a book, it's happy that they start with B. For the key rings, you can call it K, and for the pencils, you can call it P. That is why when you're dealing with colours, you are never ever given a blue disc, a brown disc, a black disc, and a beige disc, because they all begin with the letter B. You would most likely be given red, blue, green, and yellow, so that again it would help you not having to write out the full name. And similarly, when you dealing with probability, if it involves names, quite often the names are chosen so that you can use the first letter of the name. So just be aware of that. Now, here we can either write out a list of how we get the same type of prize, or we can use a tree diagram. Now, obviously, because we've got 3 prizes on for the first person to draw, then we need 3 branches to our diagram. The main thing here is that the winners of the first 2 games choose the same type of prize. So you cannot choose a book followed by another book. That is impossible. There is only one book. So technically, to be successful here in answering the question, the first person needs to choose a keyring and the second person needs to choose a keyring. Or we could have the case where the first person chooses a pencil and the second person chooses a pencil. So if we actually look at, looking at the tree diagram, what we actually have is we have a book, we have, let's make that a bit longer, we have a keyring, and we have a pencil. Well, if we've chosen the book, that means we can only choose a pencil and a keyring on the second option. From the keyring, we can choose a book, we can choose another keyring, and we can choose a pencil. And from the pencil, we can choose a book, a keyring, or another pencil. Now, I think in one sense, that's where the difficulty lies. Now, our answers that we are looking for, we need to be either at this point here, a keyring followed by a keyring, or this point here, a pencil followed by another pencil. So if we have the probability of a keyring and another keyring, the probability of selecting a keyring first time is 3/12. The probability of selecting the second keyring means we've got one keyring less, 2, but now there's only 11 objects in the bag because one of those objects. Now the symbol that goes in between them, because of the word and, we're going to put a multiply symbol in there, and that will give me 2 3s, 6 out of 132. And I'm going to leave it like that. I'm not going to simplify it at the moment. Then the other option is the probability of a pencil and another pencil. So we've got 8 over 12 times 7 over 11. There's one pencil less, so the 8 becomes a 7, and there's one item less, so the 12 becomes an 11. And that gives me 56 out of 132. So the probability of the same type of prize, so the probability of the same type, we can either get 2 keyrings, which is 6 over 132, or we can get 2 pencils, which is 56 over 132, and the symbol between them is a plus. So technically, when we start from the end point where the dot is, to get to the red asterisk, I can just follow along the tree diagram without taking my pen off the paper. But if I then decide, oh, I can get pencils, I have to take my pen off the paper to go back to the start. When I take my pen off the paper to go back to the start, that is when I will add them. So adding those two gives me 62 out of 132. And if you want, you can simplify that to 31 over 66. Sometimes with probability, it's best not to simplify the fraction until you get to the end, because you might find that one will cancel, the other one doesn't, and then you're trying to add very awkward fractions. So leave the cancelling of the fraction until the very end. Now, as you can see, for part B of the question, it says the winners of the first 3 games have chosen their prize. Find the probability that the ticket for the book is still in the box. Now, with this part of the question, do we list all the options we can have for the first 3 games that do not include the ticket, or is there an easier way? Well, it is easier if we think as we want either the book to be chosen or we do not want the book to be chosen. Now, if we go with the not book, so if we take the book, we want not a book chosen, and remember in probability, if we don't want something, we put the first letter, we put that letter and we put a horizontal line above it. So that means B stands for choosing the book. So the B with the line stands for not choosing the book. So we're not allowed to choose the book on the first one. We are not allowed to choose the book on the second one. And we are not allowed to choose the book on the third one. So it's that version we want. I'm not interested in the rest of the diagram. I do not need to add the other parts. Those are the only bits that I need to focus. So we want the probability of not a book, not a book, not a book. Now, the probability of not choosing the book on the first go is 11 over 12. There are 11 items that are not the book out of 12 possible items. We then multiply that, not choosing the book the second time, 10 items out of 11, and then finally not choosing the book on the last one is 9 out of 10. Now the nice thing about this is we can cancel down here, and if we cancel here, this 11 here cancels with this 11 here, and do it in a different color, we do it in purple. This value of 10 here cancels with this value of 10 there. So we are left with 9 over 12, which is 3/4. So we've got a 3 in 4 chance that the book is still in the box after the first 3 goes. Now, with this bonus material, it says that we're talking about Phil and his wife. Now, with this question, it tells you that the probability of Phil doing something is 0.3 and that his wife doing something is 0.6. But the probability they both eat a burger is 0.2. And then it talks about, are these events of both of them eating a burger independent, and give a reason. So you need to know the formula for an independent events. Now, in terms of that, we need the following. That if you've got two events, A and B, so Phil and Liz, P and L in this case, for independence, it means that A, and the cap sign is another word for intersection. So A intersection B, A and B occurring, is the probability of A times the probability of B. Now for this particular case, the probability of A is 0.3. The probability of B is 0.6, and the probability of A intersection B is 0.2. So if we substitute those numbers in, we've got 0.2 equals 0.3 times 0.6, so 0.2 equals 0.18. Now, as you can see, those numbers are not the same, so therefore the events of Phil and Liz eating burgers are not independent because the numbers don't match up. So events are not independent. And that's needed. Now, in terms of the mark scheme, what they've done there is they've said no. So I've said they're not independent, and then because I've shown the workings out, that's where I get the second mark. So there's one mark for stating yes, they are independent, or no, they are not independent, and then one mark for the calculation. So that's why you need to do both. And that's the end of the probability without replacement.